Hello, this is Luke. This is the next part of the series on sound detection, automating sound detection for wave files and spectrograms. And the first thing we want to do here is get a bunch of data together for the machine learning model, training data for the model. So, we want hundreds or thousands of images that we can put in to the model to train it on. So just very briefly, I'm looking for a hermit thrush song in my case, in my example, but of course you can adapt it to yours. And what I'm going to train it on is pictures, say like that, around a hermit thrush song. You can see it's already been selected as number one here. And I'm just going to take a picture of that. And that's going to be like a positive, as opposed to, say, a picture like in here, which it doesn't have a hermit thrush song, would be a negative. And so I want hundreds of different positives that are going to be boxed around the songs, and then I want hundreds, an equivalent amount of negatives that are maybe also like here, where it's only got half of a song. And we can talk about where that threshold might be between positives and negatives. And one of the interesting challenges here is that for an ordinary image classifier, you would be dealing with discrete images, but with this, we're dealing with a long spectrogram that actually isn't discrete individual images. It's just one long, big, very wide image, and we're kind of having to decide where our own cutoff is. What size of an image do we want to slice out of this? And this is kind of about making your data meaningful for whatever problem you're trying to solve. So it's kind of up to us to turn this into images that are a size that works for the machine learning model we want to build. And that really depends. If I was just trying to detect intro notes, which is what's boxed out here, then maybe my images are only this big. And I go through this and cut out little images like that, and I've actually done that as well. So you have to make that choice for yourself of what is the kind of meaningful type of image that you want, or the meaningful size of image. So I'm going over into Jupyter Notebook or Jupyter Lab here, and I want to programmatically cut images out of these files, because in our lab we happen to have hundreds of different recordings of different birds over the years that have been studied, and they all have selection tables that go with the wave files that are there, so a researcher's already selected them. And so I can use that to generate training data for my machine learning model so that I don't have to go through and generate all the data myself, which that's really important. So try to think of a way that you can get hundreds of samples of whatever you're trying to train. Sometimes on the internet you can get some code that scrapes a given database or website or something, or maybe you have your own files online. It really depends what whether you're looking for something in music that you're trying to detect, or whatever the sound file might be. So right here we've got just a few imports. These are pretty standard imports. Labrosa Labrosa might be the one that you would not see as commonly, but it's kind of for dealing with like making spectrograms and visualizing spectrograms from wave files. NumPy's super common for arrays, Matplotlib for visualizing stuff, Pandas is for data frames, and then PIL is the image library that I'll be using to generate the images. And I've just got a couple file names down here just to work with, and these are one's a wave file you can see, and that's just the recording, and then I've got the selection table that corresponds to that recording. So similar to what you're seeing here, there's a selection table down below that actually designates where these boxes are. And really all I'm interested in is the list of start times for each of these boxes. I just kind of want to have when did this song begin? This hermit thrush song, at number 5. Well, it began right there. And so I just want that time, and thankfully I'm going to get that time from from the selection table. You can see begin times is a column, and it's going to have all of the beginning times of all these boxes. So I've got a couple functions here that I figured I'd just copy paste in here that I use. One just does the Fourier transform. It creates the spectrogram. So I've kind of got a standardized little function that does that for me. And then the other one just displays a spectrogram, or a chunk of a spectrogram. And again, I've got kind of some specifics that I like to work with. So I'll try to keep it, I try not to use too much copy and pasting and stuff because I don't think that's as useful, but I thought I'd just bring those in because they're very basic. So the one thing I wanted to get first is I want to get the spectrogram. So I'm going to do the Fourier transform with wave name. And that actually takes a few seconds to run because it has to take that whole wave file and do a Fourier transform and turn it into an array. So if we look at that array, essentially what we're looking at here is just a 2D array of pixels. So if you can imagine, when you look at this, every pixel is a number from faint to dark, or like white to black in this case, and you can use different colors. But every pixel is a number that designates how loud the sound is at that frequency and at that moment in time. And all we've done here is we've visualized it in a NumPy array, and that's essentially what a spectrogram is. So you can see at this moment we're at minus 60 decibels, and then at the next moment, whatever that moment is, it's slightly quieter, that pixel, and it's gonna, this is actually huge. If we look at the shape of this, we can see that it's 623 rows, so not a lot of rows in terms of different frequencies, but it's very long, 154,000 columns. And the first thing I want to do is just figure out how long one of these columns is. I want to be able to go between time and my spectrogram, and I want to be able to do that pretty seamlessly, because different spectrograms have different resolutions depending on how you do the Fourier transform and depending on what you want. Like you might want to prioritize timing rather than frequency. And so it's important to kind of be able to work between time and columns with these arrays. And so what I'm going to do is just get a conversion ratio or a column ratio here, and I'm going to use that as a number moving forward, so that I don't have to keep thinking about it as like an abstract concept, and instead I can just be like, okay, I've got my conversion ratio, and anytime I want to go from columns to seconds, I can do it myself. I'm not reliant on some library that's kind of operating kind of behind a curtain or something. I want to be, if I'm doing some kind of analysis and filtering and we're slicing up arrays or spectrograms, I want to be in charge of kind of how big of a slice and how I'm moving between units. Otherwise, I find I can make a lot of stupid mistakes if I'm not kind of the one driving the bus in that regard. So I'm just going to get let's say the duration. So in Labrosa, there's a get duration function, and we can see there. So it's 3,576 seconds. That's close to an hour, right? 3,600 is an hour. And what I want to do is I'm going to take how many columns are in this. So let's say the number of columns equals spec. That's our spectrogram is spec, and we want to get the length of one of the rows, and that'll give us how many columns there are. So if we do that, okay, so there we go. That's the same number we saw in the shape right here. That's good. That's what we should see. And so I want to create this conversion ratio, which is just going to be how many columns I have divided by the amount of seconds there are in the recording. And here we go. So now I know that there are 43 columns per second. And so anytime moving forward I want to work with this stuff, I can know, okay, there's 43 columns per second, and I can just use this number with the decimals so that I don't get, accumulation error or something like that. This is a lot of decimals, so it's going to be pretty accurate. So that's great. And now what I can do is I can actually look at some of this spectrogram. So I've got my function up above that is display spec, and our spectrogram is spec, and let's say we want to look at 300 seconds, and we want to look at, say, 30 seconds of it, and I've got my conversion ratio, and I can do that, and sure enough, it's going to use matplotlib to show that section of the spectrogram. And then if I want to zoom in on it further, maybe I don't want it to be 30 seconds, maybe just 10 seconds. Now I'm zoomed in on that location. And let's say I want to move over a little bit. You can see that it starts at 300 seconds, but the song actually starts, more like around 302. So now we've left aligned it, and maybe I want to zoom in even further, and now I've got it kind of here, and it's left aligned even better than that, and there we go. Now I've kind of zoomed in on the song. So I can move these figures around to zoom in on whatever part of my spectrogram I want to look at. And now what I'm going to do is I want to take my selection table with all this different start times, because I already know where all these songs are from that selection table. So I'm just going to get rid of that, and I'm going to bring in my Raven selection table. So I'm going to read that in. The variable I have for the name is just the file name is table name, and I got to remember that it's separated. And this is just true of Raven tables. They're separated by tabs. Otherwise, we won't get the right look. It won't know where to divide up the values. So here's my Raven table, or just a sample of it, and I want this beginning times. I want that as an array, and so I'm going to grab those. I'll call it start times, and I'm going to go Raven table. Let's get that column. I got to make sure I write that correctly, and I'm going to turn that into a NumPy array. And the last thing I'm going to do is I'm going to sort that, because they're not necessarily sorted on the other one. And let's see. So now I've got this array, and it's all my start times of all my songs from that recording, which is now what I want to work with. So I can demonstrate that by making a for loop that iterates through this and displays all the spectrograms, and they'll all be songs. And I don't think I'll do all of them, because that's just that'll take too long and not really be nice to look at. But what we can do is just iterate through this, and I can take this same code for displaying the spectrogram. It's always good to look at, make sure you check in on your data and make sure things are still working the way you expect. So instead of that time, I'm going to actually use the time as I iterate through in this for loop. I'm going to iterate through all these start times and keep inserting a new time in each spot. And let's say if I is greater than 4, we're going to break it. So I don't show, I don't show an endless amount. And sure enough, we can see that this is the first 4 spectrograms of the hermit thrush songs. You can hopefully see, if you don't know what a hermit thrush song looks like, well, this is what they look like on a spectrogram. It's actually not 4, and that's just because the way the for loop works is it's greater than 4, so it's running 5 and 0, so I think it actually ends up being 6 here, which makes sense. Always good to, if you see something like that, you expected, say, 4 spectrograms because you put a 4 here and then you get 6. It is good to pause and be like, well, why is that happening? Because sometimes it's because you did something wrong, and sometimes it's just because you didn't understand or you didn't stop and think about how for loops work.